Sorry. All right. Let's go through this real quick. The purpose of this quiz, number one, make sure you're on time. Number two, just trying to kind of give you an idea of what to expect in terms of quizzes. And just kind of like my expectation of where you should be at this point, right? So as long as every time you come in and take quiz and you feel comfortable with it, then you're on a good track. All right, real quick, derivative of this. So the derivative here, we have to apply the chain rule. So first we need derivative of the outer function, which is the inverse sine. The formula for that is 1 over the square root of 1 minus whatever the argument is squared, right? So we need in here the x cubed minus 4x squared underneath the root like that. And then, chain rule, you have to then multiply by the derivative of what's inside. So times 3x squared minus 4 in parentheses. And you could slide that up top if you want, but that's the derivative. All right, that's the first one. The second one is to find the equation of the equation of the tangent line to this curve at this point. So the equation of the tangent line, we have to do implicit differentiation, right? There are some problems on your homework like that. So you have first to take the derivative of this implicitly. So derivative of the left side, well, chain rule again, right? Derivative of inverse tangent of something is 1 over 1 plus whatever was in there, the argument squared. So the argument in that is 2x plus y squared times, now the derivative of the argument, so there's two terms, I can do them one by one, and I'm differentiating with respect to x. So derivative of 2x with respect to x is just 2. And then plus the derivative of y with respect to x is dy dx. You can also put y prime there, that's fine. Okay, that's done with the left side. Equals now the derivative of the right side, which is a product rule. So you have to do derivative of this times this plus derivative of this times this. So derivative of x is 1 times y plus derivative of y, which is dy dx, times x. That's your product rule. So that is your implicit. Now, you need to go find what the value of dy dx is at the point 0, 0. So you could go try and solve for dy dx here, but I suggested in class that you don't do that, and that you just plug 0 in for x and 0 in for y right here into this. So I'm going to replace all my x's with 0, all my y's with 0, and that makes this 0. 0 squared is 0, and 0 plus 1 is 1. So this whole thing is a 1. Right, so 1 times, then here 2 plus dy dx, and then equals over here 1 times 0, 0, and then 1 plus dy dx times 0. This is all 0. This whole thing is 0. And on the left side, you just get 2 plus dy dx is 0, and solve for dy dx, subtract 2 on both sides. Dy dx is negative 2. That's the slope of the tangent line. You need the equation of the tangent line. So the equation, you have to come back over here to y minus y1 equals m times x minus x1, replacing y1 and x1 with 0. So y minus 0 equals the slope, which we just found is negative 2, x minus 0. At the end of the day, it turns out to be y equals negative 2x. I know at least one of you got it. Maybe more than one, but at least one of you got it. Question? No?
Well, where did we derive that right side from?
This?
Yes.
The equation of a line.
Okay.
Right? So in Cal 1, we use this like a lot, right? Anytime we want to find the equation of any line, we use that formula. And the slope for us is the derivative at some given point. All right, so we'll see. Yes?
So what's important to remember here is if you're doing the derivative here, basically you're trying to find the line to the tangent. You said is it always the case that you're going to input the points before you do or rather than instead of solving for dy dx?
So if I had given you this problem and I didn't give you a point and I just said, hey, look at this curve, find dy dx. Find the derivative of this, this curve with respect to x, you would have still done this step, but then you would have had to have got dy dx by itself on one side of the equation, algebraically moving things around. Okay, which is fine. But here, because I'm giving you a point and I'm asking you for the equation of the tangent line, all you need to know is what the value of this equation becomes when you replace x with 0 and x with y. So there's, wait, sorry, x with 0 and y with 0. So all you have to do is replace all your x's and y's with zeros and then go solve for dy dx. It's easier to do it that way.
So we weren't supposed to plug in the inverse tangent to cancel them both out and switch it to the other side?
You could have maybe done that. You could have taken tangent on both sides to start, but you're still going to have to differentiate. Did you differentiate that? I mean, you could have taken tangent on both sides, and then your left side would have been 2x plus y. Your right side would have been tangent of x, y. Then you do implicit differentiation. You could have done it that way, yeah.
Okay. Would I have gotten the right answer if I did it that way?
You would have gotten the right answer,
Okay.
yeah. Yes?
Elephant in the room, do you do partial credit on quizzes?
Yeah, so this is the first quiz, right? So I'm going to definitely be a little bit lenient on this one. I'm really going to be counting this first one more, right? Like, you need to have gotten this. This one, you know, I won't weight as heavily, I guess. Unless you got this one right and the first one wrong. I'll just kind of look at it. I'm going to be a little lenient on this one. But like I said, this is the expectation, right? My expectation is that you could come in and do these problems. Maybe you make a little mistake in here, you know, forget to move something, but you understand what you're doing. Yes?
So in regards to like partial credit in general, what's your criteria for that for exams? Like,
Well, I give partial credit. I'm not sure about criteria.
so like, because you mentioned like neatness and things like that before, so I guess you kind of look at it like a holistic thing, like is it legible?
Yeah.
Can you follow along?
Can I follow what you're doing? Can I, if you made a mistake, can I see it? Can I see where the mistake is? Can I see what you did wrong? Because that will dictate how much I'm going to take off. So if I can't read it and I can't follow it and it's wrong, I'm going to take off a lot more points than if I can read it, I can follow and say, oh, there's the problem, right? The rest of it seemed okay. I can see like how far off you are on it, you know? So every problem is going to be a little different how I grade it. I usually grade every problem on a test as if it was worth 10 points. That's the way I normally look at, you know, like every problem is like on a 10-point scale, and so you either get the full 10 points or you get 2 points taken off or 3 or, you know, the only way to get like full 10 points off is if you just leave it blank, right? If you put something meaningful down, not like a picture. Some people draw me pictures, you know, like, hi, how you doing? You know, sometimes I'll give you a point for that, but you know what I mean? Like, it needs to be something. It's hard to get minus 10 unless you go blank. Like, leave it empty. So do something if you can, I mean. All right, let's move into the next section. Hey, if you didn't do well, it's the first quiz, right? But at the same time, it's the first quiz, so, you know, we want to make sure we're ready when we come in, right? That was based on the homework, so, yeah.
I know it's hard to answer, but by the end of the class, about how many quizzes do you think we would have had?
Hopefully 10.
Like by the end of the class?
By the end, in 16 weeks, I hope to get 10 quizzes in.
I was thinking it'd be a little bit.
Yeah.
For Cal 1 last semester, there was like this many grades available for a quiz. I think we didn't do the last two.
Yeah, I have them in the grade book, and then if we get to them, we get to them, you know. Every class is different. Yes, sir?
Do you drop stuff?
I might drop, if we do enough quizzes, I may drop 1 or 2, depending on how many we do. Like if we only get through 6 quizzes, then you're probably not going to get one dropped. So even though you don't want more quizzes, it's better because you get more chance to have one thrown out. Okay? All right, we're going to do a section now. We did 3.5 last time, and the idea behind 3.5 was that we went back to pre-cal. I'm going to put it over here. We went back, we said, okay, we had sine x, cosine x, tangent x, right? Cosecant x, secant x, cotangent x. We had all of our 6 trig functions, all of these derivatives we learned in Cal 1, right? And then all of these functions have inverses. All the inverse functions have derivatives as well, and that's what we did last class, right? So we've got 12 functions, right? 6, those derivatives, right? And then another 6 functions, their inverses, and those derivatives. So we have 12 derivatives so far of trig stuff, yes? 3.6 in the book is going to cover a new type of function that I know my Cal 1 students, we didn't talk about this, so this is new. This new type of function called a hyperbolic function. And it's a weird function the first time you see it. All right, so I'm going to show you something first. I'll try and develop what it is in a minute, but let me just kind of show you something. It might be hard for you to see that. Can you all see the string hanging from here? Do you all see that? Okay, and sorry, it's the only string I had in my office. So this right here, imagine this is like a wire hanging between 2 poles, electric wire, electricity power lines, whatever. You've got this wire suspended between 2 poles. The question is there a function that models this curve? Is there a function that we've ever learned before that models this? It looks like a parabola, yeah? It looks like a parabola. So what I've done here is in Desmos, I've created an interactive parabola where what I can do is I can adjust the conditions. So this is the function I have Desmos graphing. F of x is a times x minus h squared plus k, which is the standard form or vertex form of a parabola. Okay, that's a vertex form of a parabola. And so what I'm doing is in Desmos, I'm able to adjust a, h, and k. H and k dictate the vertex, where the vertex is, and the a dictates the shape. And so what I'm going to try and do is see if I can manipulate a and h and k to see if I can get that parabola to line up with the curve or not. And that would sort of convince me that, yeah, this is a parabola. So let me first move this up a little bit. Close enough. Let me try and spread it out. Gee. Come on, I can't do it. Okay, that's good. What do y'all think? Eh? Close enough, right? Close enough? Well, in the real world, that's not close enough. Okay? There's problems. It's close, but I've got gaps, right? So maybe I move it up and I try and reshape it. No matter what I do, I'm never going to be able to lay a parabola on top of this curve. Like if this is truly a wire hanging between 2 poles, there is no parabola that would go right on top of it. All right? So that shape is not parabolic, is what I'm getting at. It's something else. This is just to kind of see if I can convince you. It's not very convincing, but I can show you what does work. Okay? It's a different type of function. It's not a parabola. It's what we call a hyperbolic cosine function, which is what this section is about. So let me show you the hyperbolic cosine function. And I didn't try this before class because I knew that in this room it would look a little different. Let me take the parabola out. Let me see. I need to move this thing around. Hold on. What's my C? Get my C. There we go. Okay, and then my A. Ah, shit. Okay, so I'm not going to go anymore, but do you see that this is less, this looks visually like it's better than that parabola was? Well, this is actually the true shape of a wire that hangs. It's called a catenary. That's what we call that shape. catenary, all right? Now, I have to wave my hands at this a little bit because to prove to you that a hyperbolic cosine function is in fact a catenary, like that catenary is in fact the shape of a hanging wire, to prove that to you requires things that we have not done yet. All right, so we have to look at the arc length of things, which we don't have a formula for yet. We haven't even studied. We also have to do some physics, static equilibrium problems where you do sum of forces in both, the horizontal and directions. You have to know something about how to do free body diagrams. So I can't prove, you're going to have to just take this on faith that this function is in fact, and you have to be able to do some differential equations, which is not even in this class. So unfortunately, I can't prove it to you, all right? I can't. You're just going to have to believe it. So let's talk about the functions, all right? Let's actually get into them. I want to show you, though, remind you, where is it? I wanted to remind you, and I can take this off of here. This is a pretty high-tech demo here, huh? There you go. I wanted to show you and remind you about the trig functions, right? Our trig functions, these came from the unit circle, right? We first talked about trig functions, we define it with the right triangle, SOHCAHTOA, and then later we say, let's do it a different way, let's look at it in terms of a circle. So if I have a circle here, if this is the angle theta, this is the unit circle, has a length of 1, then the x and y coordinates can be defined by cosine of theta and sine of theta, right? That's the way we define them off the unit circle. So as you change this angle, right, so if I change the angle, whatever this distance from here to here is, that is x, right? But that is cosine of that angle. And then this distance from here to here, that's your y coordinate, but that is sine of theta. And everything we have is based upon that, right? Like all this idea is based upon that picture. Also, the equation of this circle, the equation of it is x squared plus y squared equals 1. Does that look familiar to you? That's the equation of a circle that's centered at the origin with a radius of 1. And then what we do is actually, you know that very important identity in pre-cal, sine squared theta plus cosine squared theta equals 1, is just this right here. That's all it is, right? Replace x with cosine theta, replace y with sine theta, and you have the Pythagorean identity, right? So there's all this stuff that we developed in pre-cal, right, and in Cal 1 based upon this idea. But it's all based on the circle, right? And this equation. Well, there's another equation that we can look at other than the circle, and it's that graph. And you may look at that and you be like, wait a minute, hold on, how is that at all connected to a circle? Well, it's not connected to a circle, but the equation of that graph is very similar to the equation of that circle, with one exception. It has a minus instead of a plus. And when you graph this, you get what's called a hyperbola, right? That's a hyperbola. That's what we call it, right?
That's the equation to a hyperbola.
That's the equation of a hyperbola. Actually, that's what I typed into Desmos, and it graphed that for me, all right? If I typed in this with a plus, it draws the circle, the unit circle. But I draw it with the minus, it draws that, all right?
Inverse circle.
It's not really an inverse circle. It's a hyperbola. It's a hyperbola. It's a hyperbola, yeah. I mean, there's a precise definition of what a hyperbola is. Just like a circle, you say, is like all the points that are equidistant from a center point. You know, like there's a definition for hyperbola as well.
Would this be considered, like, not to be all physics, but like, would this be considered a fourth dimensional circle or something?
Nope. Mm-mm. We're still in 2 space. It's, yep. All right. So now, you know how in the circle just a second ago I had this, and then we said a point on that circle, we had this angle theta, and then the x and the y coordinate were just cosine and sine, right? Cosine and sine. Well, I'm going to do something similar here. If I go here and I call that angle theta, so imagine that point can move along here, right? Along this hyperbola. If I change the angle, I'm going to be at a different point, aren't I? Well, by definition, this x and y coordinate are not, obviously they're not cosine theta and sine theta, right? But they are cosine h theta and sine h theta. That is the hyperbolic cosine function and the hyperbolic sine function. So as you move theta, the value of this x is dictated by this hyperbolic trigonometric function, which I still have not precisely defined for you. I'm just trying to get you to see the similarity between that and this picture, right? The x and y coordinates are cosine and sine respectively. Here on a hyperbola, change the angle, the x and the y coordinates are cosine hyperbolic and sine hyperbolic respectively. Got it? Yes?
Does the inside of the hyperbolic function, that angle that you drew,
Uh-huh.
is like the largest, well, for this specific way that's drawn, is the largest like angle it can get is approaching like 45-degree angle?
45?
Yeah.
Let me counter your question with a question, all right? So what if our angle is 0? Where are we? If the angle is 0, we're here, right?
Yeah.
What's the x and y coordinate here? What's the x coordinate? 1. Y coordinate? 0. Okay. So that implies that at angle 0, cosine hyperbolic is, what's the value of this function at 0? 1. And what's the value of that at 0? 0, right? So this implies that cosine hyperbolic of 0 is 1 and sine hyperbolic of 0 is 0. Y'all with me? I'm getting to your question. So now let's start to increase that angle. As we increase this angle, right? Well, why am I doing it there? I can do it on here. That's why I made this. Okay. So as I increase the angle, right? Now, my angle's, whatever, 45, whatever you want it to be. What has happened to the x coordinate? It's gotten bigger, right? And the y coordinate has gotten bigger. And as this angle gets bigger, what happens to both the x and the y coordinates? They get bigger and bigger and bigger, right? Right? So as the argument, see the thing, this is the thing we're going to plug into the cosine hyperbolic. As that angle gets bigger, right, the x and the y coordinates both get bigger. Now, theoretically here, what happens here as we go to there? Can we, imagine we're right before 90 degrees. Imagine we're right in here. What do you think? Can we be here? Right. I think that's that's getting to your question, right?
Yes and no.
So you have to go back. How many of you studied hyperbolas in college algebra? I don't think, a little bit. We don't do conic sections the way we used to in college algebra. We used to spend a lot of time in them. There's actually it's like what's called a slant asymptote that goes through here. So there is an angle we can't get past. Yeah, it's not always 45, depends on the hyperbola. Okay, I don't want to get ourselves buried too much in this. I just want you to see where the idea of a hyperbolic cosine or sine function comes from. It comes from a drawing of hyperbola and the x and the y coordinate, all right? Yep.
Is this a conic section?
Yes, a hyperbola is a conic section, yes. Just like a circle is a conic section, right? Parabola is a conic section. Hyperbola is when you take the conic sections like this. There's your conic section, right? And you slice it right here. Right there, you get a little thing in here like this, and you get a little thing down here. Except mine's sideways. What? Yes?
What would the x value? Yeah, what would the x value be if the angle was 89 degrees?
Well, that's what I'm saying. We can't always go to 89 degrees because there's an asymptote that cuts through here. Look, let me zoom out. Do you see if I zoom out, there's this angle I can't go past?
Yeah.
Okay. Now, it's 45 here, it's 45 degrees here, but generally speaking, it depends on the hyperbola, because hyperbolas can have different shapes. So, like circles can be bigger or smaller. If we talk about the unit circle, that's one case. Talk about this hyperbola, this is the case, but it can change. Yep. Yep.
Earlier you mentioned cosine and sine, but we only saw cosine on there.
Sine was the y-coordinate.
Sine was the y.
Yes.
Where's the angle from? Is it,
It's the same angle.
it just stays 90?
Same angle. Yeah. What do you mean where's the angle on there? The angle was from the x-axis to the point.
Same angle, you're just using different sides of the triangle.
You say that,
The angle is right here.
Okay, so that could be sine also, that angle?
No, hyperbolic sine is this y value.
Okay,
Hyperbolic cosine is the x value
okay.
to get to that point. Go back to the circle, right? If you have an angle, right? If you have an angle, cosine is the x-coordinate, sine is the y-coordinate. Now look at the red angle. Cosine hyperbolic is the x-coordinate, sine hyperbolic is the y-coordinate.
Cosine theta is coming from the origin. I'm trying to figure out in my mind
Cosine theta is here.
where sine theta
Sine theta is here.
is the top.
Distance. It's this length from here to here.
it's the same angle.
It's the same angle.
Same angle for both sine and cosine. Okay.
Yeah.
That's what I was wondering.
Yeah.
And the angle would be theta, right?
In this case, I'm using theta, yeah.
Yeah. Or the variable.
Whatever variable I want to call it. I could call it theta. We actually wind up calling it x, which makes everything confusing. All right, so here they are. I've told you kind of where they come from. You know, hanging wire, I can't prove to you the hanging wire. Now, the precise definition, because with sine, we have a precise definition. Sine of an angle off a right triangle is opposite over hypotenuse. But if you're on a circle, it's the sine is the y-coordinate divided by the radius. So there's precise definitions for sine and cosine, but not hyperbolics yet. So here are the precise definitions for sine and cosine hyperbolic right there. And when you look at it, you're going to be like, what? Huh? Are they what?
Are they on the?
Oh, they are on your formula sheets. Yes, they are on your formula sheets. Now, I'm going to write them down because it's just worth me writing it and talking through it. We are defining hyperbolic sine function. And when you say this, you can either say sine hyperbolic or you can say hyperbolic sine. It doesn't matter what order, people understand what you're saying. Sine hyperbolic of x is equal to e to the x minus e to the negative x over 2. Or you could take that 2 and take it out in front as a fraction, 1/2, and then write it as e to the x minus e to the negative x. So it's really strange, and again, I can't really show you that without a lot more stuff, but the hyperbolic sine function is defined to just be the difference of two exponential functions.
Is there
Right.
a preference of which like notation is going to be better than using?
I think you should be comfortable with both. Me personally, I prefer the second one.
Okay.
Because in calculus, we like to pull constants out front. We don't like to deal with fractions, right? Just bring constants out front when we can. Right? So that's your definition of hyperbolic sine. Let's plug something into it just to make sure we understand how this works. Let's plug 0 into this function. Do you remember my picture a second ago? What did we say? What was sine hyperbolic at 0? Do you remember?
1.
It was 0, right?
Yeah.
On this picture, right, when we took this angle down to 0, right right there, when I take the angle to 0, this point, the y-coordinate is 0. So we should get 0 here. We should. Let's see. Well, just replace your x's with 0. E to the 0 minus e to the negative 0. Well, negative 0 is still 0, right? What's e to the 0? 1 minus e to the 0. 1 minus 1, 0, half of 0 is 0. So this is 0, right? Okay. Well, at least that makes some sense. All right, what if I did sine hyperbolic of 5? What would happen? Well, it would be 1/2 e to the 5th minus e to the negative 5, right, like that. Now I need a calculator, right, because e to the 5th is a weird number, and this one right here, keep in mind, this e to the negative 5 is actually 1 over e to the positive 5, isn't it? And e to the 5th power is a big number. So 1 divided by a big number is a small number. So do you see that this is going to be a big number minus a small number? Big minus small. So that should be a pretty big number when we're done. And if I let this number get bigger, what happens? Like imagine instead of 5, we do 50. E to the 50 would be huge, right? And then this would be really small. So it would get bigger, right? So the bigger this number gets, the bigger this value gets. Let's try cosine hyperbolic. So what is the difference between these two formulas? There's only one tiny little difference between these two formulas. That minus is a plus. That's it. That's the only difference. So the difference between that and cosine hyperbolic is that that's a plus sign right there. That's it. The way I remember it is sine is the subtract, right? Sine, subtract. And then the other one's just the add, right? Okay. All right, so that changes this to a plus. Let's try this. What should the answer be according to our picture? What should cosine hyperbolic of 0 be? Should be 1, shouldn't it? Remember, because it was, all right, let's try it. If we plug in 0 into this, e to the 0, but this time plus e to the 0, right? Or e to the negative 0. That's 1, that's 1. 1 plus 1 is 2. So you get half of 2 is 1. Okay? All right.
E to the power of 0 is 1?
Yes.
Is that true for e or true for everything?
Any number to the 0 is 1 except for 0 to the 0, which is undefined.
Okay.
Unless you're taking a limit and you get 0 to 0, then you have to do logarithmic, you got to do logarithmic stuff.
Got it.
Yes?
Is kind of a weird question. So when like sine and cosine, they're like they're trig functions. They're functions.
Yes.
So, but like the equation for a circle is x squared plus y squared equals 1.
Mm-hmm.
And so like you can't call that a function because it fails the vertical line test. But
That's right.
So like, I kind of don't know what I'm asking. But like, what would you call that? Like you just called it an equation?
Yeah.
At that point?
A relationship. It's a relationship between x and y, right?
Yeah.
When you take the equation x squared plus y squared equals 1, the graph of that is the unit circle, which fails our traditional definition of a function, like saying that y is a function of x. Right? That fails, because it fails a vertical line test. But you can still say that this is a relation, right? This is a relationship between x and y. So we just call it a relation. It's an equation that creates a relationship between two variables.
Yeah, I guess like kind of what my question is that like we can make